Hello everyone, welcome to Dr. A classes for BTech students. In today's lesson, we will explore the concept of a drainage basin that plays vital role in collecting, channeling and distributing water across landscapes, shaping both natural and human environments. Understanding hydrology is crucial for civil engineering students as it plays a key role in water resource management, flood control, irrigation planning, and sustainable development. So let us begin our journey into the science of water. Learning objectives of the course is analyzing the relationship between different components of a drainage basin, evaluating the impact of human activities on drainage basin processes, understanding the importance of drainage basin in water resource management, describing basin characteristics and their role in controlling water flow and sediment transport, explaining the concept of stream geometry and its significance in hydrology, identifying and exploring the factors that influence the water balance of a drainage basin, for example, climate, land use, human activities, etc. What is a drainage basin? A drainage basin or watershed or catchment is an area of land where all precipitation collects and drains into a common outlet such as a river, a lake, or an ocean. Key components of a drainage basins are watershed divide. It is the boundary separating different drainage basins, tributaries, smaller streams that feed into the main river channel, the primary conduit for water flow, confluence of rivers, the point where two streams meet, mouth of the drainage basin, the end point where the river discharges into another water body. Drainage basins characteristics. Key drainage basin characteristics that influence water flow and hydrology are drainage area, divide, that is watershed divide, stream order, drainage density, basin shape and its impact, slope and relief, and runoff and infiltration. Understanding these hydrological characteristics is crucial for water resource management, flood control, and environmental planning. By analyzing drainage area, stream order, drainage density, and other parameters, we can predict how a river system responds to a rainfall and human activities. Drainage area. The drainage area refers to the total surface area that contributes runoff to a river system. Larger drainage areas collect more precipitation and typically have greater discharge. This area determines the volume of water available for stream flow, influencing river dynamics and flood potential. Divide or watershed divide. A divide is the elevated boundary that separates one drainage basin from another. It can be a mountain ridge, hill, or other high landforms. Water falling on opposite side of a divide flows into different river systems. Stream order. Stream order is a method of classifying streams based on their position in the drainage hierarchy. Australia's stream order system is commonly used. It is first order, smallest stream with no tributaries. Second order, formed by two first order streams. Third order, two second order streams combined, etc. Higher order streams carry more water but responds more slowly to rainfall events than lower order streams. Drainage density. Drainage density of a catchment is calculated as drainage density equals to total stream length divided by drainage area. High drainage density, many streams in a small area, suggest impermeable surfaces, steep slopes, and high runoff. Low drainage density suggests permeable soil, gentle slope, and greater infiltration. Basin shape and its impact. The shape of a drainage basin influences how quickly water reaches the outlet. Elongated basin, water takes longer to concentrate, leading to lower peak discharge. Circular basin, water reaches the outlet more quickly, increasing the risk of flash floods. Understanding basin shape helps in flood prediction and river management. Slope and relief. Slope refers to the steepness of the land, while relief is the elevation difference within the basin. Steeper slopes result in faster runoff, higher stream velocity, increased erosion and sediment transport, whereas gentle slopes allow more infiltration, reducing flood risk. Runoff and infiltration. Runoff is the portion of precipitation that flows over the land surface into streams. Infiltration is the process where water seeps into the ground. Factors affecting runoff and infiltration include soil type. Sandy soil promote infiltration, clay soils generate more runoff. Vegetation. Dense vegetation enhances infiltration and reduces surface runoff. Land use. Urbanization increases impermeable surfaces, leading to higher runoff and greater flood risk. Stream geometry. Stream geometry refers to the physical dimension and shape of river channels, which play a crucial role in determining water flow dynamics and sediment transport processes. Understanding these aspects is essential for managing river systems effectively. Key aspects include channel shape. The cross-sectional shape of a stream channel influences water velocity and sediment movement. Channel shape is influenced by factors such as bedrock resistance, sediment supply, and flow characteristics. Stream gradient, the slope or steepness of a stream channel. Higher gradients result in faster moving water and greater erosion potential. Lower gradients favor sediment deposition and meandering channel patterns. Discharge, the volume of water passing through a given cross section per unit time, measured in cubic meter per second or cubic feet per second. Influenced by precipitation, groundwater input, and watershed characteristics. Meanders, bend or curves in a river channel that develop due to lateral erosion and deposition. Meandering rivers form in low gradient areas where water flow is slower. The presence of meanders affect flow velocity, sediment deposition, and floodplain formation. Sediment load. The total amount of sediment transported by a stream include bed load, large particles rolling along the bottom, suspended load, fine particles carried in the water column, and dissolved load, minerals dissolved in water. Sediment load is influenced by stream velocity, channel shape, and upstream erosion process. Flood plains, flat low-lying areas adjacent to a river that experience periodic flooding serve as natural buffers for floodwaters and play a role in sediment deposition, rich in nutrients, making them valuable for agriculture and water ecosystem. Water balance. Water balance refers to the equilibrium between water inputs outputs, and storage within a given system, such as a watershed or a drainage basin. The general water balance equation states that all inflows minus all outflows is equal to change in storage. This equation ensures that the total amount of water entering an area minus the total water leaving equals the change in water storage over a given time period. Mathematically, it is expressed as P minus Q plus E is equal to delta S. P stands for precipitation. This is the total input of water into our system. It comes from various sources: rain, snow, hail, sleet, anything that falls from the sky. Q represents runoff. This is the water that does not soak into ground immediately. It flows over land, eventually making its way into streams, rivers, and lakes. Think of it as the water that runs off the surface after a heavy rain. E is for evaporation. This is a combined term. It covers both evaporation, the process where water changes from liquid to vapor from surfaces like soil or water bodies, and transpiration, the process where plant releases water vapor through their leaves. Evaporation is essentially the water lost back to the atmosphere. Finally, delta S represents the change in storage. This is the tricky part. It accounts for the variation in water stored within the system. This storage can be in the form of soil moisture, groundwater, in aquifers, or even in reservoirs and lakes. If delta S is positive, it means we are storing more water. If it is negative, we are losing water from the storage. Factors influencing water balance: climatic factors, temperature, precipitation pattern, and humidity impact evaporation and water availability. Land use and vegetation, forest promote infiltration and reduce runoff, while urban areas with impermeable surfaces increases runoff and lower groundwater recharge. Soil and geology: permeable soils enhances infiltration, whereas clay soils increase surface runoff. Geological formations affect groundwater storage. Topography: steep slopes lead to high runoff and erosion, whereas flat terrains support water retention and groundwater recharge. Applications of water balance. Water balance is a crucial concept in hydrology, environmental science, and water resource management. It represents the equilibrium between water input, precipitation inflows, and water output, evapotranspiration, runoff, outflows in a system. Here are some key applications. Hydrological modeling, which is used in forecasting river discharge and groundwater levels. Irrigation planning, that ensures optimal water use in farming. Watershed management, that helps in designing conservation strategies to maintain ecological balance. Urban water supply system, that balances water demand and availability in cities. Self-assessment questions. At the end of the presentation, these are self-assessment questions. Go through each question carefully. Answer these questions based on understanding of the topic. Review any concept you are unsure about. The questions are: what is drainage basin? List three characteristics of a drainage basin. What is drainage density and how does it affect runoff? What factors determine a river discharge? How does basin shape influence flood potential? Why is understanding stream geometry essential for flood management and water resource planning? How can the water balance equation be used to assess water availability in a drainage basin? Note, our next presentation will focus on solving numerical problems related to water balance. Thanks for joining this lesson on engineering hydrology today. Hope you found this presentation informative. Now don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thank you.